Good afternoon, everyone. I am Justine Joshua Ramos. I am a research member of the Smart Grid and Green Plan headed by Sir Pedraza, Sir Jordan, Sir Adonis, and Sir Luigi. And I am here this afternoon to present to you or to carry over what Sir Luigi discussed earlier. And I would like to, before I start, the screen, this presentation will be titled The Development of the Generator Dispatch Scenarios for Reference and Clean Energy Scenarios. So, like mentioned earlier, this will be a series of talks that will carry over from the previous one. So, this talk will carry over from what Sir Luigi discussed earlier. So, the main question I would like to emphasize in this talk is to simply answer a very simple question. So from the generators placed and cited and sized by the methodology discussed by Sir Luigi, we now ask ourselves how much of the generator capacity must be dispatched or how much of that generator is the output for a given scenario by year 2050, by year 2030, or at any particular scenario. So that is that is the main question I would like to address in this short talk given to me this afternoon. So, okay, so now we have a set of generators by year 2050. We placed it at different locations. We provided different sizes, capacities, etc. We now have to know how much of that generator must be scheduled. So it might be a very simple question, but it is quite a complex one because we must understand that there are a lot of scenarios out there. What if it is summer? What if it is evening or noon? These generators that are mainly composed of solar, wind, those variable in nature, they vary depending on time and season. So how can we exactly capture how they will behave at year 2050 provided that we have a lot of scenarios at hand? So in this talk, I will present to you the assumptions, the processes made by the team to make a very good model for these cited generators. But there is one equation located at the top showing that the total generator schedule or the total output of the schedules dispatched must always be equal to the demand by year 2050. And this is important for us to proceed with the power flow analysis that will be discussed by Sir Adonis later on. So, So this is just a rough methodology of the process. So the input of the dispatch scheduling process is the site and size generators from the previous discussion. And later on, I will show to you this process in which what we call clustering, the second box up there. Because yes, like what Sir Pedraza mentioned earlier, that we want to design a model that can handle the extreme scenarios of the Philippine grid by year 2050. We cannot naively say that, okay, solar generators can always be at the maximum output during summertime. We cannot naively say that solar generators are at zero output during non-summer months. Because we know that, yes, during summer months, solar generators provide high output, but we cannot say that those are equal to the maximum capacity of the solar panels. So we ask the question, the big question of how high is high and how low is low. So that is the part being answered of the VRE clustering process. Beyond that, we try to schedule those generators that are not variable in nature, particularly coal, nat gas, batteries, oil. We try to schedule them by keeping in mind that we must always have an equal demand and generator schedule. And at the end of this discussion, the output will be handed out to multiple power flow analysis methods, in particular the DC power flow method that will be discussed later on. So whenever I say these scenarios, for me to just shed light what a scenario is, so this is just a snippet of the TDP 22 to 2040. So we can see here, I hope it can be read properly. On the first column there, we can see that there are multiple scenarios wherein they try to simulate scenarios wherein we have a maximum north, the north side of Luzon, for example, the maximum south of the Luzon, in which they are trying to say that all generators located at the north of the Luzon or south of the Luzon are at max output. So we can see that there are a lot of scenarios out there. But for the SGGP team, we summarized everything, or we tried to simplify all scenarios into 4 scenarios only. We have here the non-summer evening, the non-summer noon, summer evening, and summer noon. So we see here that we mainly used the difference in time, season, in our dispatch cases. So this is one of the process we did to schedule those generators that are variable in nature. This is the clustering process I mentioned earlier, wherein the coordinates determined by the sizing process from the last talk, we use that as an input to get the historical data for solar and wind profiles from different locations in the Philippines. After that, we entered that into our VRE clustering process program developed by the team, in which we try to answer the question how high of the solar generators must be dispatched, how high of the wind generators must be dispatched. Okay? So this is the result of that process. So let me just introduce this plot shown in the screen. So the x-axis, or the horizontal axis, shows the different solar, wind locations. So that's location 1, location 2, location 3. While the vertical axis, or the y-axis, shows the generator output. So notice that there are a lot of orange strands out there on the plot. And each of those orange strands right there represent historical solar and wind data from year 2021 to 2022. So each orange strand out there is an hourly data from 2021 to 2022. So what we did is that we determined the best representative scenario, or the best representative output for solar and wind out of those thousands of data from those 2 years mentioned earlier. So that technique is what we call the clustering technique, or in a more technical sense, the K-medoids process. So from here, we now try to dispatch the dispatchable generators, namely the coal, natural gas, hydro, etc. And in this table right here, we present the dispatch rules to determine which generators must be prioritized to fill up the demand. So please take note that the list there is presents a hierarchy, meaning we prioritize those that are in level 1. Then we go down as we try to fill up the load. And take note that is not a random order. There is a reason behind it. So for example, the topmost level belongs to solar and wind, because we cannot really control the amount of solar and wind outputs. The next one, we see that we dispatch the minimum output of coal and nat gas plants, because we have to ensure that in a network, there must always be inertia in the system. We have to ensure that there are actual generators running in the system. So notice that we can go farther down to oil and battery, just to fill up the demand. So in the succeeding slides right here, I will just present a simple process, a simple example of how we apply the dispatch rules to fill up a sample demand. In this case, we have here 48 gigawatts of demand at the lowest column. So the first column shows the list of generator technologies. The second column shows an example total capacity of those technologies. The third column shows the actual schedule for that particular generator technology. And the fourth column shows the percent dispatch for that certain generator type. So let's try to go through the hierarchy presented in the table. So the first one, the level 1, shows that we scheduled the solar and wind. So let's try to do that. So as a result of the clustering technique I presented earlier, the results says na, okay, we dispatched 75% of solar, as shown in the fourth column, and 52% of the wind generators, and 100% of the run-off river plants. And if we total the outputs at the bottom, it is still at 30 gigawatts. So it is still insufficient to complete the 48 gigawatt demand. So after that, we proceed to the next level, which is level 2. in which case we dispatch the minimum output of our coal and nat gas plants, which is at 30%. So notice that we added there 30% for nat gas and coal, but we see that the total schedule is still insufficient to supply the 48 gigawatt demand. So we proceed farther down the table. So we proceed with the geothermal, hydro, and biomass. So it's still not enough until we reach level 4, in which we try to complete the demand using our coal and nat gas plants. So we see here now we stop at level 4. We no longer have to dispatch oil and battery because we already satisfied the demand. So that is just a quick sample of how we do the dispatch rules, how we schedule the generators presented by Sir Luigi earlier. And this is now the final result of the process. So if you'll notice along the second column, it is a bunch of bus numbers. But in the project, those are actual Philippine buses. No? So we just replaced the names there. And the other column shows how much of the generators connected at those buses must be dispatched at a particular scenario. So this is now the data that will be transferred to the next presenter, no, Sir Adonis, for the DC power flow analysis. So to summarize everything, what we presented here is that a continuation of the generator sized and cited from the previous talk, wherein we answered how much of those cited generators must be scheduled for a particular scenario, while keeping in mind that the total generation must always be equal to the total demand. We also presented that for us to schedule those generators that are variable in nature, namely solar and wind, we undergo a certain technique called the clustering technique, because we have to know how much, or we have to know how high is high and how low is low. And lastly, dispatch scenarios, dispatch rules, there are a lot of them, no, that can be adapted for any particular scenario. And we presented a one sample process of how we do it in the SGGP project. So with that, I thank everyone for the short time given to me. I hope everyone has a great afternoon. No? Thank you so much, everyone.
Thank you, Joshua. Any question from the floor? Sige, kung wala, Joshua, I'll award to you this certificate of appreciation. Can you start over there? Certificate of appreciation presented to Justine Joshua Ramos for his presentation on development of generator dispatch scenarios for reference in clean energy scenarios, NISCON 2024.